So in this session we will be discussing about WKB approximation method. So WKB approximation is the abbreviation. WKB is the approximation of three scientists named as Wenzel, Kramers and Berlin. So these are the three scientists who has devised this approximation method. Usually this approximation method is used to solve simple one-dimensional Schrodinger equation problems. Okay, so especially the bound state problems which you might have seen in the 5th semester or undergraduate quantum mechanical courses, especially this bound state or tunneling problems. All these kind of problems will be using this WKB approximation method. So let's assume that a particle of energy E is moving in through what you call a potential, let us say V of x. So the particle is having an energy E which is moving under a potential V of x which is constant. So suppose if E is greater than V, in that case the wave function, which we know we have derived the same in undergraduate classes, the wave function will be of the form e raised to plus or minus I kx, where the plus wave, that means the plus wave function is the wave which moves in the right direction and the minus sign indicates the minus x direction. Okay, usually the wave function is a superposition of these two waves. All right, here k is, as you know, k is simply root of 2m e minus v by h cross. So this is the thing. Now comes the question. These are familiar ideas for you. Now suppose v of x is not a constant. Suppose that v of x is not a constant but varies slowly, in comparison to lambda, where lambda is, as you know, lambda is 2 pi by k, right? 2 pi by k. So comparing to the lambda, if v is varying very slowly, in that case the wavelength, there are many waves. So if v of x is varying very slowly compared to the lambda, then essentially this v of x can be treated as a constant. Then it is reasonable to suppose that psi remains practically sinusoidal. എന്ന് പറഞ്ഞാൽ ഇതേ സൊല്യൂഷൻ ടൈപ്പ് തന്നെ നമുക്ക് അവിടെ യൂസ് ചെയ്യാൻ കഴിയുന്നു. പ്രാക്ടിക്കലി ദ psi remains sinusoidal except that the wavelength and amplitude changes slowly with x. Okay, so let's go for the problem so that you will be understanding the problem in details. Okay, suppose, before that, suppose in some cases, suppose E is less than V. In that case, the psi, as you know, psi takes the form of exponential function. Okay, here the k is usually root of 2m into v minus e by h cross. So that is the idea behind this. Now suppose now consider a system here. Okay, so here the potential varies. Now you have an energy, let us say this is the energy of the particle. Now suppose this is the shape of the potential. Okay, so here we know that the potential is not a constant. Now there are 2 points where E is equal to V and in between these points, let us say x1 and x2. In between x1 and x2, E is greater than V, obviously. Alright, you can see that from here. At x1 and x2, E is equal to V, and x less than x1 and x2, x greater than x2, those cases V is greater than E. Okay, so this region, where E is greater than V or V is less than E, those regions are usually called the classical region. Those regions are usually called the classical region. Okay, so now the Schrodinger equation is, what is the Schrodinger equation? As you remember, Schrodinger's time independent equation can be written as h cross square by 2m. Okay, this is one dimensional problem which we are dealing with, so that is dou square by dou x square psi plus v of x psi is equal to E psi. That's the Schrodinger equation, let's say. Okay, now this equation can be rearranged. Let's rearrange this. Dou square psi by dou x square is equal to E minus V, right, into psi, okay, 2m by h cross square minus, right. Then this 2m into E minus V, this usually we call it as p square. So this now I can write minus p square by h cross square psi. So dou square psi by dou x square. This is another form of Schrodinger equation. Let's say equation number 2. Okay. So now we can say that since E is greater than V, alright, so here E is greater than V in the classical region which we are considering. So here like 2m E minus V, so this is a positive quantity because E is greater than V. So in that case, P is a positive number, so P square is obviously a positive number. So this is called a classical region. Okay, so now in those cases the psi can be represented as, okay, so see this equation can be very easily solved, but still, okay, so in those cases the psi can be represented as a of x, some amplitude, e raised to I phi of x. Here phi of x is some phase, okay, which is a positive real number, okay, some real phase, and of course you have a real amplitude, obviously a real amplitude also. Now what is psi dash? If I am taking the derivative, so psi dash is equal to, you have two terms now, a dash e raised to I phi of x plus a I phi of x, right, sorry, now a dash e raised to phi of x, now I a phi dash e raised to I phi of x, alright, good. This is correct, no? Now what would be the second derivative? Take the whole derivative. A double dash e raised to I phi of x plus a dash I phi dash of x into a dash, okay, a dash I phi dash into e raised to I phi of x plus I a phi double dash I a phi double dash e raised to I phi of x minus, yeah, I over minus a phi dash square e raised to I phi of x. Right. Okay. So let's put all these things back into the equation, our familiar equation number 2. So put this back into the equation number 2, you will be getting a double dash plus these are I made a mistake. Okay, just let me check. I need some term here. So a double dash e raised to I phi of x plus a dash I phi dash e raised to I phi of x plus I, okay, oh, this a dash I missed, okay, so there is another term also here, I a dash phi dash e raised to I, ഇതിൻ്റെ a dash എടുക്കാൻ മറന്നുപോയി, okay, so phi of x, okay, so this becomes 2, so that I missed it, sorry, these 2, so I can now write 2I a dash phi dash, a dash phi dash, നമുക്ക് ലാസ്റ്റ് ഇ റേസ് ടു ഐ ഫൈ എന്നുള്ള ലാസ്റ്റ് എടുക്കാം, പ്ലസ് ഐ എ ഫൈ ഡബിൾ ഡാഷ് മൈനസ് എ ഫൈ ഡാഷ് സ്ക്വയർ ഓൾ ഇൻറ്റു ഇ റേസ് ടു ഐ ഫൈ is equal to minus p square by h cos square psi. What is psi? Psi is a e raised to I phi. Okay. Okay. Now this has a real terms as well as imaginary term, but on the right hand side you have only real term. So let's equate the real terms. That means a double dash minus a phi dash square is equal to minus p square by h cross square a. Right? Correct. So a double dash is equal to a into phi dash square minus p square by h cross square. And similarly 2a dash phi dash plus a phi double dash is equal to 0. I'm just equating the imaginary parts. So this equation I'm just rewriting, just check it. This equation I can write as if a square phi dash or dash, alright, is equal to 0. Suppose if I take the this is correct, no? So that becomes 2a dash. So just take it, okay. This is 2a dash phi dash plus a square phi double dash is equal to 0. Just cutting the a, so this is 2a phi dash plus a phi dash. So this I can write. Now a square phi dash is equal to some constant, should be or phi, a square phi is equal to, so a square phi dash is equal to c square. A square phi dash is equal to c square. Let's say a is equal to c divided by root of phi dash. Right, good. So some constant c. Okay. So so we got one equation. Let's say this is number 3. So we got a. Let's check the first this equation. Okay, this cannot be solved in general. It's a very difficult equation to solve if you check that in case. So we assume that the a varies very slowly, so that a double dash is negligible. We assume that the amplitude, varies slowly, so that a double dash is negligible. Okay, so in that case what will happen? Phi dash square is equal to p square by h cross square. Look, this 0 this 0 this becomes 0. I mean, it can be cancelled. So this is 0. That means phi dash square is equal to p square by h cross square. And what is phi dash is equal to plus or minus p by h cross. Good. Because we need phi dash. Already we need this phi dash for a കണ്ടുപിടിക്കാൻ already ഒരു root phi dash അവിടെ ഉണ്ട്. അതുകൊണ്ട് തന്നെ നമുക്ക് എന്ത് ആവശ്യമുണ്ട്? Phi dashനെ ആവശ്യമുണ്ട്. So now I can write phi is equal to, okay, dou phi by dou x is equal to plus or minus p by h cross, or phi is equal to 1 by h cross plus or minus integral p of x dx. Correct? So that now we got the phi, we got the c, we got the a, sorry, not c, we got the a and everything. So now I can write psi is equal to a e raised to phi I phi x, alright, I phi of x, which we have used. So a we got it as c divided by root of p of x, because phi dash is equal to okay, p of p by h cross. Let's say p by h cross, no problem. H cross. Then this h cross can be absorbed into c, no problem. Okay, so that's what I am writing here. Then e raised to plus or minus I by h cross I by h cross phi of x, I by h cross integral p of x dx. So this h cross can be absorbed into c, so this is c divided by root of p of x e raised to plus or minus I by h cross integral p of x dx. So that is the psi you will be looking for. Is it clear? So if I normalize this, you can find out the psi, I mean c and everything. Okay, so no problem. So this is how we will be finding out the wave function in a problem like this. Let's go for the tunneling. First example as tunneling. So okay, as the problem says, the psi of x can be approximated as c divided by root of. Okay, now there is a problem here. See, what is the tunneling? Here the particle will be having an energy, but the potential barrier will be higher than this. So that means E will be less than V. Correct? So if E is less than V, what will happen to P? Because we have defined the P as, so I'll show you the P which we have defined. P is simply 2mE minus V. Right? So when E is less than V, this becomes negative. So one I will come. So this is going to be a complex function. P of x is going to be a complex function. So in that case, we will take the mode of P of x e raised to plus or minus. Already the P of x is complex, so some I comes out, so that now it becomes 1 by h cross integral P of x dx. Okay, so no problem. I'll show you. So so let's consider some bumpy potential barrier. Okay, you have a wall like this. Okay, so this is the V of x. Now a particle comes, this is the energy level, the particle energy is this. Okay, so in this region, let us say 0 to A, in this region 0 to A, the potential is higher than the energy of the particle. So on the left hand side you have two waves, one incoming wave and one reflected wave. So this wave can be for x less than 0, I can write the wave function psi of x is equal to a e raised to I kx plus b e raised to minus I kx. Good. What is the k? Here the potential is 0. So k can be very simple. K is equal to root of 2me by h cross. So that is it. And what about the right side? Here only the outgoing wave will be there, no reflection anything. And of course in this region also, in this 1, let us say 2 and 3. Okay, in the third region also the potential is 0. So in that region also I can write psi is equal to, let us say, f e raised to only plus, because it's only going outside. Okay, kx. So that's the other region. So the transmission probability is simply f square divided by s square. Now what about the intermediate region? The intermediate region, that means in between 0 and a, here the potential is higher. So that the wave function should be some c, okay, mod pxy, because p of x is a complex number. Okay, e raised to 1 by h cross, okay, let us say 0 to a p of x dx plus d. ഇതിനകത്ത് കൂടെ വേണമെങ്കിൽ എന്ത് ചെയ്യാൻ പറ്റും, ഇതിനകത്തുകൂടെ ഇങ്ങോട്ടും പോവാം, വേണമെങ്കിൽ ഇവിടെ നിന്ന് റിഫ്ലക്റ്റ് ചെയ്യുകയും ചെയ്യാം. സോ ദാറ്റ്സ് വൈ വി ഹാവ് എ നെഗറ്റീവ് ടേം ഓൾസോ. ഡിവൈഡ് ബൈ റൂട്ട് ഓഫ് mod p of x e raised to minus 1 by h cross integral 0 to a p of x dx. Simple. Okay, so that's it. So that is the one way of this is the wave function inside it. Okay, now f by a, you have to find out the f by a. So the relative amplitudes of the incident, that means here you have an incident wave, usually that is a. Okay, so you have an incident wave and transmitted wave. So ഈ നോൺ ക്ലാസിക്കൽ റീജിയൻ, ഇതിനാണ് നോൺ ക്ലാസിക്കൽ റീജിയൻ എന്ന് പറയുന്നത് അല്ലേ, ഇവിടെ ക്ലാസിക്കൽ അല്ല റീജിയൻ. സോ ഈ നോൺ ക്ലാസിക്കൽ റീജിയണിൽ എത്രമാത്രം കുറവുണ്ടായി എന്നതിനെ അപേക്ഷിച്ചിട്ടല്ലേ ഇവിടെ പുറത്തു വരുള്ളൂ. അത് ഇങ്ങോട്ട് കുറച്ച് വരുന്നു, അതിൽ നിന്ന് കുറച്ച് പുറത്തു വരുന്നു. പക്ഷേ ഇവിടെ എത്രമാത്രം തടയപ്പെടുന്നു എന്നതിനനുസരിച്ചല്ല ഇവിടേക്ക് പുറത്തു വരുന്നതും ഇങ്ങോട്ട് വരുന്നതും തമ്മിലുള്ള റേഷ്യോ ഉണ്ടാവുക. സോ എസെൻഷ്യലി now this f by a, അതായത് ട്രാൻസ്മിറ്റഡ് ബൈ ഇൻകമിങ് എന്ന് പറയുന്നത് ഈ നോൺ ക്ലാസിക്കൽ റീജിയണിൽ എത്ര റിഫ്ലക്റ്റ് ചെയ്ത് പോയി എന്നുള്ളതിനനുസരിച്ചല്ലേ, അതിന് പ്രൊപ്പോർഷണൽ ആയിരിക്കില്ലേ. സോ നൗ ഐ ക്യാൻ റൈറ്റ് ദാറ്റ് ഈസ് സിംപ്ലി ഇ റേസ് ടു minus 1 by h cross integral 0 to a p of x dx അല്ലേ. It's something proportional to or almost equal to എന്ന് പറയാൻ പറ്റും. Okay, so that is it. Now the transmission coefficient is the square of this, so this is almost equal to e raised to minus 2 1 by h cross square, okay, integral 0 to a p of x dx. Correct? Good. So that is how we will be doing it. Okay, so that's the first part. Okay, thank you.